Then how these catalysts are working. So absorption of a reactant at an active site. First they will absorb the reactants at the active site. That which leads to a catalytical action. Active site is refers to the place where the reaction can occur or reactant are absorbed, and this can result bond within the reactant molecule and which become weaker, and the molecule being held in more reactive configuration. So there will be also higher concentration of a reactant at a solid surface, which leads to higher collision and greater rate of reaction. The transition metal can use the 3D and 4s of atom on the metal surface to form a weak bond with the reactant. Basically, how they are weakening the bond or strength of this bond. As you know, the transition element, they have d orbital and s orbital. D orbital is partially filled. So example, in this d orbital, first they will occupy singly and then they will pair up. So if the bond is there, like example, I'm giving example like formation of ammonia by in a Haber process. So what happened? These are also electrons. So these electrons are also experience attraction from the empty d orbital and empty s orbital. And due to this attraction between the empty d orbital and s orbital, the bond will become weaker. So what are the steps in heterogeneous catalyst? Reactant form a bond with atom at an active site on the surface. As a result, the bond of reactant are weakened. New bond formed between the reactant head closer together and on the catalyst surface, so that this will turn or this will weaken the bond between the product and the catalyst and leave the. So basically what happened, the last point. So first the reactant form a bond with atoms at an active site. So first reactants are attracted active site, they will form a bond. As a result, bond in the reactant are weakened and break. So bond become weaker and it can break. So it can react and form a product. And the new bonds between the reactant which held closer to or on the surface of the catalyst. So basically what happened, like there's an attraction between the transition element and the reactant molecule. But when nitrogen is reacting, nitrogen is forming a bond from other side. So new bond formed between the reactant held close together on the catalyst, and this in turn weaken the bond between the product. So there will be a weak bond, the new product and the catalyst and the product leave each other so the product can escape. So basically what happened, first you have a catalyst, that catalyst trap example hydrogen. On the surface it absorbs hydrogen molecules. When nitrogen will form a bond, ammonia is there, and because the bond between nitrogen and hydrogen is stronger than this bond, so the catalyst will break the bond with hydrogen and the product will escape. Is it clear how the heterogeneous catalyst works? Any doubt in this? Any doubt? Okay. So when you check the oxidation number of vanadium in V2O5, so one oxygen is -2, so 5 oxygen -10. So vanadium should be +10 because compound is neutral. So each vanadium is +5. Same way in V2O4, one oxygen is -2, 4 oxygen will be -8. So vanadium should be +4. +8 for total and +4 for individual. So first vanadium +5 changes to +4, but during a reaction it returned back. That's why we say it does not used up or it is acting like a catalyst, because to be a catalyst, the substance should not chemically change or remain unchanged. Same way in a car catalytic converter, because catalytic incomplete combustion of a car fuel produce carbon monoxide and oxides of nitrogen. Because of electrical discharge, oxides of nitrogen are also produced. So these catalytic converter, they absorb this carbon monoxide. So when nitrogen oxide react, it will oxidize carbon monoxide to carbon dioxide and reduce nitrogen monoxide to nitrogen. So these remove carbon monoxide, oxides of nitrogen, and unburned hydrocarbons such as octane from exhaust gases by turning them to harmless carbon dioxide, nitrogen, and water. And converters have a ceramic honeycomb coating with a thin layer of a catalyst. Basically, a ceramic is a support material for them, and it's like a honeycomb which will have a large surface area so that it can have a greater surface area to trap greater amount of reactants or reactants on the surface, which leads to greater catalytic activity. So platinum, palladium, rhodium, these are the elements which can be used on the surface of the ceramic. So the idea is that when it can trap the substance on the surface and the reaction can occur, or when it traps, it might react and form another product. Like you can see here, when it traps sulfur dioxide, it forms another product, and that further react with oxygen and form again return back the same substance. So that's why we call that as a catalyst. Copy this one. So how the homogeneous catalysts are, so when catalysts and the reactants are in the same phase, we call that as homogeneous catalyst. Homogeneous catalysts, the catalyst basically when we are using, they should have the same, they should have a same phase, and because the transition element have a tendency to form or to form a compound which have variable oxidation state, so they can oxidize or reduce during a chemical reaction and initiate a reaction. So transition metal can act as a homogeneous catalyst because they can form various oxidation state, so they are able to donate or receive electron during a chemical reaction. So what happened, like example you are taking for homogeneous catalyst. So reaction is there between iodine and S2 and O8, and it is catalyzed by iron 2. So how this is catalyzed by iron 2? This is the overall reaction S2O8 with a charge of -2 react with iodine, changes into iodine molecule and sulfate ion. But how iron is helping this reaction to occur at a faster rate? So first what happened, because if you have iron 2, so uncatalyzed reaction is very slow because the reaction need a collision between the two negative ion. This is S2O8 negative ion. I-1 is also negative. So first two negative ions have to collide to form a product. So if negative ions will collide, because like charges repel, so it is difficult for them to collide by themselves. So we need a lot of or greater amount of energy, or it means that this reaction will have a higher activation energy. But if we add a substance which contain iron 2, so first what happened, iron 2 is a positive ion, S2O8 is a negative ion. So S2O8 will change into SO4 and iron 2 will change into iron 3 because it is donating its electron. So iron 2 changes to iron 3. And then what happened? The iron 3 is there an iodine, so iron 3 will take electron from iodine and again change back to iron 2. So you can see here the tendency of this substance to be oxidized and reduced help in speeding up this reaction. So both the individual stage is catalyzed mechanism involve a collision between a positive and negative ion, which lower the activation energy, or reaction can occur at a lower temperature. So for a substance to act as a homogeneous catalyst, its electrode potential must lie between the potential of the two reactants. Like otherwise what happened if both cases, because iron 2 is changing into iron 3 and iron 3 is changing back into iron 2. So the electrode potential is the voltage which is produced when the substance gain electron, that's called electrode potential. If it is positive, that substance tend to gain easily. If it is negative, then the substance tend to lose. So both cases, the electrode potential should be feasible for reaction to occur. Maybe iron 3 changes to iron 2, but the electrode potential was too high, then the reaction may not occur. So for a substance to act as a homogeneous catalyst, the electrode potential of the two reactants, so its electrode potential must lie between the two reactants. So it is first reduced and with a more positive electrode potential, and in the second step, it is oxidized with a more negative electrode potential. Because what happened, like example, electrode potentials are always negative. So if I say electrode potential for S2O8 changes to SO4 because it is gaining electron here. When you write for sulfur, overall, this is when you write the oxidation number for sulfur in S2O8 with the overall charge of -2. So one oxygen is -2, so for 8 oxygen will be -16. So what should be this? This should be +14, because so the total should be -2. And if total is +14, so one should be +7. So in this case, the sulfur is +7. And in sulfate already we know, because one oxygen is -2, so 4 oxygen will be -8. So sulfur should be +6. So +7 changes to +6. How +7 will change to +6? By gain of electron. So it should gain electron, so that now if electrode potential are given for S2O8 with a charge -2, and say the electrode potential is -1.1 volt or +1.1 volt, and for iron 2 to changes into iron 3, so iron 2 gain electron and changes into iron 3, the electrode potential is given minus, or not minus, you can take say +0.3. So when you check which one have a tendency to gain electron easily, this one have tendency to gain electron. The equation, it will be +3 to +2 by mistake. So +3 changes to +2 by gaining electron, because electrode potentials are always given to gain electron. So which of them can gain electron easily? The first one can gain electron easily, and in this case, iron 3 changes to iron 2 gain electron is less likely to occur. So what will happen? Will the reaction occur? Yes, there will be a reaction, because iron 3 changes to iron 2 by gain of electron, the electrode potential is 0.3. And when S2O8 gain electron change to SO4 with the charge -2, electrode potential is +1.1. So higher electrode potential for this. If electrode potential is higher, so means that substance can gain electron easily. So if this substance can gain electron, so the other substance should lose electron. So opposite will happen. So iron 2 loses electron and change to iron 3. But when you compare this with iodide, like iodide ion, iodine atom gain electron and change to iodide ion. So when you compare these two example, if this was 0.1, so when you're comparing these two, then which one have a greater tendency to gain electron? Iron 3 will have greater tendency to gain electron. So this will happen same way, and this equation will be opposite. So the electrode potentials will also decide which substance will be oxidized and reduced. Is it clear? So the first, so it can first reduce the reactant with more positive electrode potential, and then oxidize, then in the second step oxidize the reactant with more negative electrode potential or smaller electrode potential. So means when iron 2 is reacting, the electrode potential of iron 2 and iron 3 should be less than S2O8. But in the second reaction, the electrode potential should be higher than iodide ion so that it can convert. Is it clear? Any doubt in this?
Yes.
Next, the following reaction is catalyzed by cobalt ion in acidic solution. Write a mechanism for catalyzed reaction by writing two equations involve cobalt 2 and cobalt 3. So first what we will do, like we should identify the equations, because what happened here, this is the equation which is given. So first we will divide this equation into two halves. How we'll divide this equation? We'll divide into oxidation half and reduction half. And it is in acidic medium. So what are the reactants? So SO3 and SO4. So you can see here SO3 we separate with SO4, and oxygen is there, is the second reactant. It changes into water. From where you can get these equations? You can get these equations from the data booklet. You don't have to memorize anything. You can get from data booklet, or there's also another way. If you remember AS, if you want to balance a redox equation, so how we balance a redox equation? Like if I say I have half O2 and I want to balance this equation, because the overall, first I'll write the overall equation. The overall equation was SO3 changes to SO4 and half O2. Okay. SO3 reacted with half oxygen changes to SO4. Sulfate ion, and the valency for SO3 is -2. So if I divide this equation, I will divide into reactant. So SO3 is there. If SO3 is a reactant, so SO3 can form SO4. With a charge of -2. Same way, if oxygen is there, but for oxygen there is no reactant mentioned here. For oxygen, no reactant mentioned, but we can know if oxygen is there and we want to balance a redox equation, we add by water. So if half oxygen means one oxygen is there, we'll add one water. And if we want to balance a proton, so if we want to balance a hydrogen, we add proton. If you remember AS, balancing a redox equation, if you want to balance oxygen, you add water. If you want to balance hydrogen, you add proton. And then to balance the charge, how to balance the charge? Here the charge is +2. So I can reduce the charge only, so I add 2 electrons in this side. Same way, 3 oxygen, 4 oxygen, so I will add 1 water molecule. So that is balance. I will add 2 proton other side, so hydrogen will be balanced. And I will, here the overall charge is -2, here charge is +2, -2, 0. So I should add 2 electrons on this side. And I will add the 2 equations, so I will have the final equation. So first we split the 2 equations into half, and oxidation and reduction half, you can see here. Oxidation and reduction half. So to balance oxygen, we add water. To balance hydrogen, we add proton, and then we balance the charge by adding electrons. Now, what we have to use as a catalyst, cobalt-2. So cobalt-2 should be used as a catalyst. So how cobalt-2 can be used as a catalyst? Because cobalt-2 can lose electron and change to cobalt-3. And cobalt-3 can gain electron and change to cobalt-2. This is the overall equation. So in this reaction, if you check the first reaction, means it is gaining electron. So from where it will gain electron? It will gain electron from cobalt-2. When cobalt-2 lose electron, it will turn into cobalt-3. But why we add 2 cobalts? Because this 1 cobalt will provide 1 electron, so 2 cobalt will provide 2 electron. Or how I can write a simple equation between them? This is one equation, this is another equation. If I want to write a combined equation, I'll make the number of electrons same, and I will add the 2 equations, so electron number will cancel with electron number, and I will get the equation for cobalt. Same thing, cobalt-3 is changing into cobalt-2. So if I compare with this equation, I'll multiply by 2 and add, so I will get the second equation. So this is how a cobalt is working as a catalyst for this reaction. Is it clear? Any doubt in? So basically what we did, we separate the oxidation half and reduction half. In this equation, the first equation is a gain of electrons, it's reduction. In the second equation, it's because electrons on the product side, so it's a loss of electron or oxidation. So if this is reduction, then the other substance should be oxidation. Like that, we'll take that equation and with the substance which is used as a catalyst is oxidized. And then it will be reduced.
I'm sorry, I don't get how does the sulfate ion, it doesn't get that, I mean the oxidation state doesn't change. I don't get that part.
The look, when you write for SO3, the SO3 is there with a charge of -2. So 1 oxygen is -1, 3 oxygen will be -6. So what it, because to be -2, it should be +4. So actually in SO4, the sulfite ion oxidation number of sulfur is +4. But when it forms sulfate ion, the overall charge is -2. So 1 oxygen is -2, 4 oxygen will be -8. So to be -2, it should be +6. So sulfate oxidation number is changed. Like sulfur oxidation number changes, sulfate valency does not change. Like the charge does not change. In SO3, the charge was -2. In SO4 also the charge is -2. Why the charge remains same? Because the oxidation number of sulfur changes. What is the oxidation number of sulfur? In SO3, 1 oxygen is -2, so 3 oxygen will be -6. So because we want total to be -2, so this should be +4. Same way in SO4, 1 oxygen is -2, 4 oxygen will be -8, so this should be +6. So you can see here, sulfur in sulfite ion was +4 and sulfur in sulfate ion is +6. So oxidation number of sulfur changes, but the valency or charge on the ion does not change. Is it clear?
Yes.
Less than a minute left, so you can take a screenshot for the take the picture, and you can copy this part. So this was about the heterogeneous catalyst. Tomorrow we'll discuss Kc and Kp and start a new topic.